Let's talk about the difference between molecular and empirical formula. Here are the definitions. The molecular formula shows the actual number of atoms of each element in the molecule, whereas the empirical formula shows the relative numbers or the smallest ratio of atoms of each element present in the compound. As an example, let's find the empirical formula of acetylene. Here, the molecular formula is given. So what we have to do is find the smallest ratio of moles of carbon to hydrogen. The molecular formula shows a ratio of 2 moles of carbon to 4 moles of hydrogen. And then we have to divide them by the greatest common divisor on the top and the bottom. In this case, we divide it by 2. So this gives 1 mole of carbon for every 2 moles of hydrogen. And this is the smallest ratio of moles of carbon to moles of hydrogen. So we use this ratio to write the empirical formula. 1 carbon and 2 hydrogens. And this is the empirical formula for acetylene. Next, let's define the empirical formulas for these molecular formulas. As a first example, we have glucose with this molecular formula. So we have 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So we need to divide all of these by the same greatest common divisor, which in this case is 6. Okay, so after dividing by 6, we get 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. And this becomes the empirical formula of glucose. We can see that this 1 carbon, 2 hydrogens, and 1 oxygen is right here, shown in this figure. And this is just one unit of the different units that make up the molecule of glucose. Next is acetic acid, and this is its molecular formula. In this case, we divide it by 2, and we get the empirical formula that is the same as the empirical formula of glucose. Next is lactic acid with this molecular formula. In this case, the greatest common divisor is 3, and we get the same empirical formula. Finally, we have formaldehyde with this molecular formula, and in this case, the ratio of carbon to hydrogen and oxygen is already the smallest, so we don't need to do anything. We can just write the same formula for the empirical formula. Or you can just assume that is divided by 1, which gives you the same formula. So you can see that these different molecules have the same empirical formula. And for the case of formaldehyde, which already gives you the smallest ratio of elements, the molecular and the empirical formula is the same. Next, let's define the mass percentage composition. This is the mass of each element expressed as a percentage of the total mass. For example, what is the mass percentage of hydrogen in water with this molecular formula, H2O? We're given the molar mass of water and the molar mass of hydrogen. And we have to use this formula up here to find the mass percentage of hydrogen. But first, let's define the following ratio. For every 1 mole of water molecule, we have 2 moles of hydrogen and 1 mole of oxygen. Then we can use the formula to find the mass percentage of hydrogen atoms. So for this, we have mass of hydrogen atoms divided by the mass of water molecules times 100%. So the first one, the mass of hydrogen atoms, is defined as follows. So we have 2 moles of hydrogen, and we multiply times the molar mass of hydrogen to get the mass of hydrogen. So it is multiplied times 1.0079 grams per mole of hydrogen times 100%. And all of this is divided by the mass of water molecules, which is 1 mole of H2O times 18.02 grams for every mole of H2O. Notice that units of moles cancel for hydrogen and water, and we're left with units of grams on the top and the bottom. So 2 times 1.0079 gives 2.0158 grams, and 1 times 18.02 is just 18.02 grams, and all of this is multiplied times 100%. Grams goes away with grams, and this division gives us 0.1119 times 100%, which gives us 11.19%. And this is the mass percent of hydrogen in water. To find the mass percent of oxygen in water, this is just 100% minus the other element, which is hydrogen, the number that we just found. So this gives us 88.81%. The concept of mass percentage is used to find the empirical formula, which is a common question in chemistry. You can use the following 4 easy steps to find the empirical formula from mass percentages. Let's go over the following example. We're given the mass percentage of aluminum, 52.93%, and the mass percent of oxygen, 47.07%. And we're given also their respective molar masses. Okay, so to find the empirical formula, first we have to change the percent to grams. So the 52.93% of aluminum becomes 52.93 grams of aluminum. And in the same way, the percentage of oxygen becomes 47.07 grams of oxygen. And all this is saying is that we have a total of 100 grams of compound. We just choose 100 grams because it's an easy number to work with. So this is step 1. Step 2 is to convert grams to moles. Okay, so to do that, we just multiply by their respective molar masses. So for every 1 mole of aluminum, we have 26.982 grams of aluminum. Grams and grams cancel, and we get 1.96 moles of aluminum. For the case of oxygen, for every 1 mole of oxygen, we have 15.999 grams of oxygen. Units of grams cancel, and we have units of mole of oxygen, which is 2.94. Okay, for step 3, we have to divide by the smallest number of moles. Okay, so for the case of aluminum, we have 1.96 moles. For the case of oxygen, we have 2.94 moles. The smallest mole number is the one for aluminum. So we divide both by 1.96 moles. So this one gives us 1, this one gives us 1.5. And then for the last step, we multiply by a factor that gives us the smallest whole number. So for step 4, So the oxygen ratio 1.5 is not a whole number, but the one for aluminum is a whole number. So we have to multiply by the smallest factor that gives us a whole number for both. In this case, it would be times 2. So this gives us 2 for aluminum and 3 for oxygen. And with these numbers, we write the formula: 2 for aluminum and 3 for oxygen. And this is the empirical formula for aluminum oxide. Finally, one of the most common questions in this topic is the determination of the molecular formula. We can find the molecular formula if we're given the mass percentages for each one of the elements that make up the molecular formula, just like before. Then we follow steps 1 through 4 to find the empirical formula, and we follow 3 more steps, 5 through 7, to get to the molecular formula. If we're given the empirical formula and we're asked to get the molecular formula, we can just follow the last 3 steps. As an example, let's go over this problem and find the molecular formula of caffeine following all 7 steps. So this problem reads: caffeine, a stimulant in coffee and tea, has a molar mass of 194.19 grams per mole. So let's write that down. So the molar mass of caffeine is 194.19 grams per mole of caffeine. And then we're given that the mass percentage composition of carbon, hydrogen, and nitrogen and oxygen are the ones given here. So let's write down all the percentages. So we have 49.48% of carbon, 5.19% of hydrogen, 28.85% of nitrogen, 16.48% of oxygen. And notice that adding all of these percentages here adds up to 100%. So we can easily say that we start with 100 grams of caffeine. So let's do step 1, changing from percent to grams. So changing all of these gives us 49.4 grams of carbon, 5.19 grams of hydrogen, 28.85 grams of nitrogen, 16.48 grams of oxygen. Then for step 2, we need to convert from grams to moles. So to do that, we need to multiply each one of these for their respective atomic masses. So for the first case, we have for every 1 mole of carbon, this weighs 12.01 grams of carbon. So notice that the units of carbon, grams of carbon, cancels, and we're left with units of moles of carbon. And this is 4.120 moles of carbon. For the case of hydrogen, we multiply times. For every 1 mole of hydrogen, we get 1.0079 grams of hydrogen. The units of grams of hydrogen cancels, and we're left with units of moles of hydrogen. This gives us 5.15 moles of hydrogen. For nitrogen, we have for every 1 mole of nitrogen, 14.01 grams of nitrogen. Grams and grams of nitrogen cancels, and we're left with 2.059 moles of nitrogen. Finally, for oxygen, for every 1 mole of oxygen, we have around 16 grams of oxygen. So units of grams of oxygen cancels, and we have 1.03 moles of oxygen. Next, we have step 3, where we have to divide by the smallest number of moles. So the smallest number of moles here is 1.03. So we have carbon, hydrogen, nitrogen, and oxygen. So let's write the number of moles that we got for each one of them. And then we divide all of them by 1.03, which is the smallest number of moles. And we get the following numbers. We get 4 for carbon, 5 for hydrogen, 2 for nitrogen, and 1 for oxygen. So these numbers will give us the number of moles in our empirical formula. So 4 carbon, 5 hydrogens, 2 nitrogens, and 1 oxygen. And this is the empirical formula of caffeine. So this takes care of step 4. We don't have to multiply by any factor because this already gives us the smallest ratio of moles for these elements. So with this empirical formula, let's find the molecular formula. Having found this empirical formula, we can follow the last 3 steps to get to the molecular formula. So for step 5, we have to write the empirical formula, which we just did, and find the molar mass of this empirical formula. So to do that, notice that in the empirical formula we have 4 moles of carbon, 5 moles of hydrogen, 2 moles of nitrogen, and 1 mole of oxygen. Okay, so let's use that to calculate the molar mass. So for 4 moles of carbon, we multiply by its atomic mass, which is 12 grams of carbon for every 1 mole of carbon. Then we add 5 moles of hydrogen, multiply by its molar mass, which is approximately 1 gram for every 1 mole of hydrogen. We add 2 moles of nitrogen, and we multiply times 14 grams for every mole of nitrogen. And finally, 1 mole of oxygen, multiply times 16 grams for every mole of oxygen. So notice that in every case, the units of moles cancel, and we're left with units of grams. So multiplying 4 times 12 gives us 48 grams. 5 times 1 gives us 5 grams. 2 times 14 gives us 28 grams. And 1 times 16 gives us 16 grams. And adding all of these together, we get 97 grams, and this is per mole of this empirical formula. Okay, so let's move on to the next step. For step 6, we divide the molecular mass by the empirical molar mass, and we get a factor. Okay, so we divide molar mass by the empirical molar mass, which we just found. The molar mass is the one given at the beginning of the problem, 194.19. 194.19, and this has units of grams per mole, and we divide it by 97 grams per mole, so the units cancel out. So let's just focus on getting the factor. Dividing these two numbers, we get 2. That takes care of step 6. For step 7, we multiply the empirical formula times this factor. So we have the empirical formula having 4 moles of carbon, so multiplying this times 2, we get 8 moles of carbon. And for hydrogen, we have 5 times 2, 10. For nitrogen, we have 2 times 2, 4. For oxygen, we have 1 times 2, 2. And this is the molecular formula of caffeine.